This video is going to be on section 17.5, which is factors that affect solubility. So you looked at KSP and writing those equations and calculating KSP or molar solubility, and now we're going to look at what affects that solubility. So there are a few factors that affect the solubility. There are three that we're going to focus on. So the first is the presence of a common ion. The second is the pH of the solution. And the third is the formation of complex ions and how that would affect solubility. So we're going to first look at the common ion effect. So the common ion effect says that solubility is decreased when a common ion is added. This is an example of Le Chatelier's principle that we talked about when we did equilibrium before. So we're going to look at an example of calcium fluoride. Consider the solubility of calcium fluoride. It is a slightly soluble compound, so if you put calcium fluoride into a beaker of water, it will partially dissociate into calcium 2+ and fluoride ions. If more F is added, so if we add more fluoride ions, say by adding sodium fluoride, the equilibrium will shift to the left to offset that increase. So we added more fluoride ions, and so in order to offset that, we need to use those back up, which means in order to use those back up, it will shift to the left, and more calcium fluoride solid is formed, which means precipitation occurs. Remember, precipitation is formation of a solid, so if we have too many fluoride ions, it will shift left to use those fluoride ions back up, and more calcium fluoride is formed. So we can look at this chart just to look at the trend of solubility versus having a common ion. So in general, the solubility of a slightly soluble salt, such as calcium fluoride, is decreased by the presence of a second solute that furnishes that common ion. So the more sodium fluoride you add, think about the equilibrium expression. So the more of this fluoride ion that you add, the more you have to use up, and the more calcium fluoride solid you have, which means the solubility is reduced. So now we'll take a look at the effect of pH. So if we consider a reaction of magnesium hydroxide, which is a slightly soluble salt. At equilibrium, in the beaker, it has Mg2+ ions and 2 moles of hydroxide ions. So if the hydroxide ions are removed, then the equilibrium would shift right to produce more of those hydroxide ions, and more magnesium hydroxide dissolves. So the OH- can be removed by adding a strong acid. So think about what happens when you put a strong acid into water. Well, the strong acid, let's say we had HCl, completely dissociates to give us H+ and Cl- ions. So we have H+ ions, we have Cl- ions, and what happens is these H+ ions will react with the basic anion, and it reacts with the basic anion to produce, in this case, H2O. Okay, so OH- can be removed by adding a strong acid, which lowers the pH. Another example would be if we had calcium fluoride solid at equilibrium with its ions. If we remove the F-, the equilibrium would shift right and more calcium fluoride would dissolve. And again, like before, the F- ions will react with the H+ ions of a strong acid, which lowers the pH because we're adding a strong acid. But your F- ions are used up. So these are used up, which means we have to counteract that. We have to make more by dissolving more calcium fluoride. So if we add a strong acid, so if we lower the pH, the solubility, if it contains a basic anion, increases. So like I said before, in general, the solubility of a compound that contains a basic anion, so basic anion means it's the anion of a weak acid. Okay, because think, why is it only an anion of weak acid? Well, strong acid anions are neutral. The solubility of a compound that contains a basic anion increases as H+ increases. So like before, you kind of have to think through what we're talking about. As H+ increases, pH goes down. Okay, so solubility goes up as pH goes down. But remember, buffers control pH. So if a buffer is used, there would be no change in concentration because the pH will not change. And so what you have down here at the bottom of this slide is it's just a particle diagram to show what is happening when you add a strong acid. And then it also shows, if your conjugate base is a weak acid, so this is the basic anion versus a neutral anion. So notice, if you add a strong acid to an anion that is neutral, nothing is going to happen. Okay, solubility is unaffected. So something to also make note of when you're looking at pH effect is you want to look at how basic the anion is. So the more basic the anion, the more solubility is affected. So keep that in mind as you go through practice problems. And again, neutral anions are unaffected by the pH. So the third and final thing that we're going to look at that affects solubility is the formation of what's called a complex ion. So a complex ion is formed from metal ions that can act as Lewis acids. Some metal ions can act as an acid, and they form what's called a complex ion with different bases. The formation of these ions, and this is the important part, the formation of these ions increases the solubility of the salt. So a complex ion, again, is just a metal ion that is bonded to one or more substances that has lone pairs. This can be seen with the formation of water in chapter 16. So if you have copper 2+. So if you have copper 2+, looking down at this example, this just says M+ for metal, but the metal ion can actually attract various water molecules that have lone pairs of electrons, and it solvates this metal cation. So the water molecules surround and bond to this metal ion, and that creates what's called a complex ion. So it can not only happen with water, it can also happen with cyanide or with ammonia or with hydroxide. And so these complex ions can be formed with various molecules. But just a rule of thumb with complex ions, the number of molecules, which are also called ligands. So a ligand is just a molecule that can be bonded to a central atom, like a central metal ion, but the number of molecules that a metal ion attracts is equal to double its charge. So this works about 75% of the time. So you can have, if you have a charge of 2+, you could attach 4 ligands to that. So what we'll do is take a look at this chart that you have in your notes. This just shows the formation of some complex ions. And if you take a look at the ones that have the asterisks, those are the ones that don't follow that rule of thumb that we talked about. So for example, the first row is silver ions, and it's surrounded by ammonia. So silver has a charge of +1, which means it can put 2 ammonia ligands around it. So this just shows various complex ions and how they are formed. It just shows the different types of complex ions. So with, copper 2+ with ammonia versus copper 2+ with cyanide. But notice that iron 2+ doesn't follow that rule of thumb where iron 3+ does. So you don't have to necessarily know, which ones don't follow that rule of thumb. It's just important to keep that rule of thumb in mind because it does work 75% of the time. So it can be used, as we go through all of these examples. How the complex ion formation affects solubility. If we take a look at an example of silver chloride. Silver chloride is insoluble. So it has a KSP of 1.6 times 10 to the negative 10. Very small KSP, which means not very much of it can dissolve in pure water. However, in the presence of ammonia, the solubility will greatly increase because silver ions, Ag+, will form these complex ions with ammonia. So you can take a look at this picture at the example. Notice that normally in the first picture, silver chloride is not very soluble. So not very many silver ions and chloride ions will exist in the solution. But if we put it into ammonia, so if instead of pure water we use ammonia, notice that it reduces our concentration of free Ag+ ions. It creates this complex ion, and because we can create this complex ion, that increases the solubility of AgCl. Okay, you can dissolve more AgCl in solution because you can create these complex ions out of the Ag+ ions that are formed when you dissolve more. And so then it shows you if you use enough ammonia, you can completely dissolve that AgCl that is normally insoluble. So the more complex ions you can form, the greater solubility is affected. Okay, so again, the solubility typically increases when you can form complex ions. So your book mentions amphoterism and solubility. We're not going to talk much about this, but it is good to know. Remember that amphoteric means that it could act as either an acid or a base. So if you have an amphoteric oxide or an amphoteric hydroxide, that just means that it is soluble in either strong acids or strong bases because of their ability to act as either an acid or a base. So just some examples that you might see are oxides or hydroxides of aluminum, chromium, zinc, and tin. And you can just take a look at the picture below. Aluminum hydroxide dissolves in strongly acidic solutions because of the acid-base reaction that you can have, but it also can dissolve in strongly basic solution because of complex ions. So again, if you have any questions, please write them down on your notes packet so that you can ask during the question and answer session during the beginning of class, but also please take a look at your book. Just skim through, practice examples, the figures, because your book does contain more information than this video does. So maybe just skimming through the book might answer some of your questions. But that is it for this video. So in class, you will be working on some practice problems on this. But again, if you have questions, write them down so that we can go through those.